Howdy and welcome. In this lecture video we're going to talk about rotational kinetic energy, one more step into our world of looking at things moving in a circle. So as we've seen already with the rotational world, the equation for rotational kinetic energy mirrors the equation for linear kinetic energy. That was 1/2 mv squared. So let's go ahead and call this linear, L. And for rotational kinetic energy, then we're going to have still 1/2. The rotational analog of mass is I, and the rotational analog of velocity is omega, and we're going to square it. So we have here our equation for rotational kinetic energy. Remember, all different kinds of objects have all different kinds of I's, and omega is measured in radians per second squared. You can use your nice little wormhole equation here, and remember that omega is equal to velocity over r. So we do have a v squared over r squared there as well. Now, we can then look at an example of something that is both rolling and moving translationally or linearly, and this is like a bike wheel. A bike wheel rolling on the ground without slipping. Bike wheel rolling on the ground without slipping is going to have an omega. It has a total mass, it has a radius r, and it's also going to have a linear velocity v going along the ground without slipping. And so to look at the total kinetic energy of this bike wheel, we would have to add up the linear kinetic energy plus the rotational kinetic energy. And the linear kinetic energy is going to be half the mass of the bike wheel times the velocity squared, and the rotational kinetic energy is going to be half of I. And let's go ahead and say that this is a hoop. We're going to ignore the spokes. The spokes are light enough. And I for that is going to be mr squared times omega squared. So remembering that mr squared is the rotational inertia for a hoop. Well, we can simplify this a little bit, remembering that omega here, if the wheel is not slipping, you can use the wormhole equation. Omega is equal to v over r. So let's put that in and simplify. We have half the mass times the velocity squared still, plus half mr squared times v squared over r squared. And we get some r squareds cancel. We see we have half mv squared plus another half mv squared. So we're looking at mv squared for the total kinetic energy of this bike wheel rolling along the ground without slipping. So with that in mind, a cyclist doesn't just have a kinetic energy of 1/2 mv squared when she's moving along the road. She's also got two rotating bike wheels. She's got rotating pedals as well, and gears and all that fun stuff. So we'd have to add up the rotational kinetic energy of the two wheels, of the pedals, of the gears, all that stuff that's turning in a circle, along with the total mass of the bike and the rider times 1/2 v squared. All right? So the total kinetic energy of something rotating and moving translationally is going to be bigger than 1/2 mv squared. Now, once we've got rotational kinetic energy in hand, then we can go back and look at the law of conservation of total mechanical energy for things that are rolling. So let's go back to the inclined plane. Now, something's not sliding down the inclined plane. We have something starting at the top and rolling down the inclined plane. Let's go ahead and say it starts at a height h. And we want to know, lots of questions here. What is the final linear velocity of, let's call this a hoop. And we've got an I of mr squared for the hoop. The hoop has a mass m, it's got a radius r, and it starts from rest at the top and it rolls to the bottom without slipping. So it's going to have some translational velocity at the bottom. It's also going to have some omega at the bottom. And there is friction involved in this, but the friction goes into the rolling of the wheel. Think about it. If there was no friction between the wheel and the ramp, then the object would just slide down the ramp, and we wouldn't have to consider rotation at all. There is friction. There's enough friction here so that the object rolls, and that friction doesn't take away from kinetic energy here. Essentially, you can think about the friction is applying a torque to the wheel, right here, and it's that torque that causes the wheel to rotate. So we can think about friction doing work, and that work goes into the rotational kinetic energy of the wheel. Regardless, if we say that energy is conserved, E naught is equal to E final, then initially we just have gravitational potential energy. Finally, we have rotational kinetic energy plus linear kinetic energy for this thing rolling without slipping. And again, being specific here, my gravitational potential energy is going to be 0 at the bottom of the ramp. So at the top of the ramp, we are at rest. We've got the mass of the wheel times g times h. That's going to equal the rotational kinetic energy at the bottom, which is 1/2 I times omega final plus 1/2 m times v final. And I got to square those. All right. So let's go ahead and plug in some more stuff here. For I, for a hoop, this is a hula hoop going down the ramp, let's say, we've got mr squared. Let's go ahead and plug in the wormhole equation for omega because it's rolling without slipping. We've got v squared over r squared plus 1/2 of the mass times the final velocity squared. And some simplification again, r squareds go away, and we end up with the same thing that we had in the last panel. Our total kinetic energy is going to be mv final squared. So moving that up here, we have mgh is equal to mv final squared. Masses do cancel. Remember, on the inclined plane, masses canceled out. The mass of the object didn't matter. Notice also the curious result that the radius of the hoop didn't matter either. The radius canceled out. And so we have here a similar equation to what we've seen before. But remember, every time we've done conservation of energy like this before, we've gotten square root of 2gh. This time it's just square root of gh. That's equal to the final velocity. And this is the linear velocity of the object. So another interesting question to ask is what percentage of the final kinetic energy is rotational and what percentage of the final kinetic energy is translational or linear. And we can go ahead and remember that the total kinetic energy is going to equal, going back, total kinetic energy is going to equal mgh, which is going to be mv final squared. Well, that was also equal to 1/2 of mv final squared plus 1/2 of mr squared times v final squared over r squared. So this is the linear, and this is the rotational. And when we do our little deal here, we still get 1/2 mv final squared plus 1/2 mv final squared. It's pretty easy to see. In this case, half the kinetic energy is linear, and half the kinetic energy is rotational. That would not be the same if this were a solid cylinder rolling down the ramp. It would not be the same if this were a hollow sphere rolling down the ramp. They would have different proportions of that total kinetic energy. So there's a ball rolling down the ramp. Let's take a look at something that's a little bit more complex. All right, so here we have a modified Atwood machine. One mass is hanging, it's going to fall to the ground. The other big mass is sitting on a table. Let's make it easy on ourselves and call that table frictionless. So in the linear world, once we figured out conservation of energy, we could solve an Atwood machine problem pretty much more simply with conservation of energy than we could with Newton's laws. And now we're going to add another hurdle to this. When we've done Atwood machine problems before, our pulley did not have mass. Now our pulley has mass. The mass of the pulley is mp and it has a radius r. So using rotational kinetic energy, we can now account for the mass of that pulley and get a more complete picture of the motion of this system, because most pulleys have mass. All pulleys have mass. Some can be disregarded because they're so light. So using conservation of energy here, we can say that the initial, let's not say that. Let's say that the initial energy is equal to the final energy. And we can say that because there's no friction acting here. And initially the system has gravitational potential energy. That's UG of little m. Technically, if this is our gravitational potential energy equal to 0 down here, big M does have gravitational potential energy at the start, but he's going to have the same gravitational potential energy at the end. So those are going to cross out anyway. So the only change in gravitational potential is little m. And once little m hits the ground, or just before he hits the ground, then we've got the kinetic energy of big M, we've got the kinetic energy of little m, and we have the kinetic energy of the pulley, because it will be rotating. Okay, so filling in what we have here, the potential energy of little m is going to be little m times g times y naught, his height off the ground. Backtracking, we do want to find out what is the final velocity of the system just before little m hits the ground. Okay, so that's what we're looking for here. The kinetic energy of big M is going to be 1/2 big M times v final squared. The kinetic energy of little m is going to be 1/2 little m times v final squared. They will have the same velocity. And the kinetic energy of the pulley is going to be 1/2 the I for the pulley times omega squared. And I for the pulley, let's go ahead and say that this is a solid disk. So I then is going to be 1/2 mr squared. That would be mass of the pulley times the radius of the pulley squared. So putting that in, we have mgy naught equals 1/2 big M v final squared plus 1/2 little m v final squared plus 1/2 of 1/2 mass of the pulley r squared times omega squared. We're going to assume the rope doesn't slip over the pulley, so we can use the wormhole equation, v squared over r squared. All right, so that's our complete expression for conservation of energy. We're going to be solving for this v final, and this one over here is a v final. It's the same velocity if it's rolling without slipping. So this r squared here cancels with this r squared here. The two halves here are going to make a 1/4, so let's go ahead and write that out in its entirety. Again, mgy naught is equal to 1/2 of big M v final squared plus 1/2 of little m v final squared plus 1/4 the mass of the pulley times v final squared. Notice on the right-hand side, every single one of those terms has a v final squared in it, so we can pull that out. Let's give ourselves some more room here. mgy naught is equal to v final squared times 1/2 of big M plus 1/2 of little m plus 1/4 of the mass of the pulley. Dividing both sides by the stuff in the parentheses and taking the square root, we've got our original gravitational potential divided by an expression that deals with the mass of the system. And take the square root. There's the final velocity. No, it's not pretty, but algebraically it wasn't that difficult. And take my word for it right now that it's way easier than using Newton's second law for linear motion as well as Newton's second law for rotational motion, because we'd have to take that into account. And in this case, the tension here, call this T1, is not going to equal the tension here, T2, because the pulley has mass. So you end up with 3 equations, 3 unknowns. The algebra is daunting. You get to the same place, but it's ugly. All right? One last thing. As for linear motion, the work energy theorem still holds here. Remember that the net work done on an object is equal to the change in the kinetic energy. So let's say that we've got a grinding wheel here, and it's hanging out with an initial omega of 0, and we spin it up to speed, and it's got a radius r, a mass m, and we want to know how much work was done in spinning it up to speed. Well, the work done is going to equal the change in the kinetic energy, but this time it's rotational kinetic energy. This thing's not moving. If it was a bike wheel starting at rest here on the ground, and it moves up to some final velocity here without slipping, then it's also going to have an omega final here. then the work done in getting the bike wheel to go from rest to that linear velocity and angular velocity is still going to be the change in the rotational kinetic energy. So always keep that in mind now for things that are moving linearly as well as rotating, or just for things that are rotating. That's it. See you next time.